To start recording. I'm recording now, for the record. There we go. I know we don't have a periodic table up on the wall to look at, so we drew one right there. Does that look a little different from the periodic table you're used to? Yeah, what's different about it?
It's describing them by shapes.
Okay, we've got shapes and symbols representing our elements. You mean to tell me that a straight line with two curvy bits is not a shape? What's that? Okay. It could be a shape that we just don't have the context for. Okay. So most of what Dalton's design didn't deal with the shapes we're used to. Thankfully, at least in my opinion, we switched to the alphabetic system that we currently have to represent our elements as opposed to these goofy looking shapes. Okay? But they probably aren't any more or less difficult than the symbols that we've already created. Okay? What else do you notice? There's a whole hell of a lot less elements up there, aren't there? Okay? Our periodic table has 118. What is that? 24? Okay. I didn't actually count that. So for those of you counting, I see you. Okay. Why are there less? They just hadn't discovered them yet. They hadn't been able to purify, get them into a state that allowed them to identify what those specific elements were. But they were able to come up with a system to describe this. This is cool because now we can potentially build these things and we can connect these symbols to each other. How do we know they're chemically linked? Might be nice to look at an example. There's an example in the purple box. Those are chemically linked. How do we know they're chemically linked? They touch each other. That same spacing that we use now between H2O to figure out that it's water and not hydrogen and oxygen is also used in this system. It's just the spacing of those objects. Okay? As we push further through his rules, all atoms of an element are identical and have the same properties. So that means when I look at an atom of hydrogen pulled from water versus an atom of hydrogen pulled from hydrogen gas, those atoms have the exact same properties. Okay? That's the assumption going into this. Rule 3. Atoms of different elements combine to form compounds. That's what our purple box is. In fact, that's what that whole bottom section is referencing. We can combine those elements to make compounds. Okay? Those compounds combine in small whole number ratios. It's kind of a corollary, which for the record, I don't really know what a corollary is, of Rule 1. Corollary is like a secondary piece, right? Something like that. From Rule 1, we know 4 is probably true. Okay? We can combine to make larger compounds. They must combine in whole number ratios. How do I know they must combine in whole number ratios? Rule 1, they're indestructible. I can't break them apart. Okay? So it's kind of a necessary piece based off of Rule 1. And then 5, atoms can combine in more than one ratio to form different compounds. Okay? 2 people walked into a bar. The first one ordered a glass of H2O. The other one said, I'll have a glass of H2O too. The second one died. But that one, yeah, okay. Okay? We can get different compounds using the same elements, but just different ratios. And it can drastically change the end result. Okay? So that was Dalton in early 1800s, starting to draw some conclusions. Okay? From 1800 probably up to early 1900, we see an explosion, potentially literally, of discovery of elements. Lots of different elements come out. Okay? And people start actually looking for and trying to find them and come up with patterns to represent them as consistently as possible. Okay? The next real big discovery we get is Thompson, who comes in with a model of the atom right, in early or late 1800. So 1890s, 1903, something like that. right? And he really pushes two big discoveries: negatively charged electrons and positively charged protons. He found things smaller than atoms. What we have now is the birth of subatomic particles. Okay? What does that mean about Dalton's rules? They were wrong. Okay? We heard one that was right. There are some that are right. There's some that are wrong. So somebody else other than who shouted out wrong, which one was wrong? The first one said we couldn't break them apart. They're indestructible. Thompson disproves that. Okay? We know our atoms are made up now of these particles. Okay? What I think is neat about this is that this discovery hinged on a big advance in technology. Early or late 1800s. What do you think that discovery might be? A vacuum. We actually needed a vacuum, and not a vacuum to clean up, okay? Because that was probably the end application of it, but a vacuum to create a tube where there was nothing in it. That means there were no atoms in it. Okay? And at the same time, we're playing around with electricity, so we wanted to see if electricity could move, and that's when we started to know what made up electricity. And we get cathode ray tubes, okay, or cathode ray guns as they were initially set up, okay, which are tubes that have been put under massive vacuum pressures. There's virtually nothing inside it. And then we put a big electric current behind it. Well, if there's nothing in it, what happens when I put electricity on it? Nothing. Nothing should happen. And instead what they noticed is this weird, eerie glow started to appear. Okay? Added on top of that, they noticed that if a magnet was placed on different sides of the tube, what happened to the glow? It moved. Okay? So whatever that thing was that was causing that glow was charged, and it was not an atom because we'd removed it all using a vacuum. Okay? We now have existence of electrons. Okay? Because we know when we walk around through nature, we don't just randomly get shocked frequently. Because I know of the existence of electrons, I also know the existence of protons to cancel that charge. Okay? So I now have the building blocks. Okay? So Thompson takes this and says, okay, we need a new model of the atom. Our atoms must be made up of these electrons and protons, okay, or these negative and positively charged things. Okay? And that model that he went through and built is what he called the Plum pudding model. Okay? In that plum pudding, he just said our atoms are a sea of positive charge, and the electrons are these negative plums floating in it. Okay? Which sounds kind of like a silly model, but maybe if we were British and we enjoyed plum pudding, it would make more sense. Okay? Since we aren't, we just think it's a bit silly. But that's all we've really had to go on. We have negative, we have positive, and we know atoms exist. So somehow let's bring these pieces together. Okay? Some people already started to throw out some terms, and you did some reading. What do we know exists in an atom? What else is there? Neutrons and a nucleus. What is the nucleus? So where all the protons and neutrons exist. What happens when I put a positive charge near a positive charge? For those of you who are like, I don't really know. Take a north end of a magnet and the north end of a magnet. Bring them near each other. They repel. Like charges repel. Thompson knew that. Why would he put all of the positive charge or all of the negative charge in one spot when he knows all they're going to do is repel away from each other? So this model within that context makes a decent amount of sense. Okay? Initially, he could only come up with mass to charge ratios, so he could come up with the relationship of charges between protons and electrons. So when we say the proton is positive 1 and the electron is negative 1, that's relative charge. There's no unit associated with that. Okay? Whatever positive value the proton has, the electron has the same value, but negative. And that was really all he could discover. Before we dig, I think, too much, let's make sure I got it right, into continuing to build that theory, I like referencing this experiment, which is not in the textbook. Okay? But what I want you to get out of this experiment is not the numbers at the bottom, but the science behind this. Okay? So there's a couple big science things that come out of this. So we get Millikan and Fletcher design this experiment. Okay? I always get them backwards. I think Millikan was the primary investigator and Fletcher was the postdoc or graduate student. The way graduate science works is you join a lab, the lab manager tells you what to do, you do it. You get great results. You tell the lab manager and they go, great results. And what does the lab manager do? Take the results, put their name on it, ta-da, look at how fancy I am. And what do they get? A Nobel Prize. Ta-da! Millikan gets a Nobel Prize. Fletcher gets pretty much nothing. Okay? But that's roughly how science currently works. To my understanding and the little bit of digging I've done on this, that dynamic was a little bit different. Fletcher came into the group and said, this is what I want to do. This is how I'm going to do it. And Millikan said, go for it. That sounds brilliant. So Fletcher did almost all of the legwork behind the experiment, and yet Millikan still gets the results for it. Okay? So it's just kind of an interesting insight into science as a research. Okay? But now let's actually drill into the experiment itself. Okay? It's called the oil drop experiment. So we take a little perfume bottle, you squeeze that, and it sprays stuff, right? See the little droplets? And droplets go everywhere. It's the whole point of it, right? Okay, they took a box and sprayed into the box. Where do the droplets go? Down. They just fall downwards. Okay? Well, they poked a tiny hole at the bottom of the box. When they spray, what are the odds anything's going to go through that hole? Minimal. Slim to none. But every so often, a single drop will fall through that hole. Okay? Underneath that hole, they put up a capacitor. Okay? And all a capacitor does is it builds charge across it. Okay? And they put up a microscope at the other end of it so they could look through this long tunnel, roughly focused where that oil drop is supposed to fall through. So someone sits there with their eye to a microscope, squeezes a little perfume bottle, and waits to see a drop. When the drop goes through the hole, now the action comes into play. And that capacitor, that buildup of charge, okay? We get a positive charge up here and a negative charge here. We dial a little knob to change the amount of charge. Okay? So what happens is that electron, which we know to be what charge? Negative, falls through that hole. What does it see? What's at the bottom of that hole? There's our hole. As I start to fall down, what do I see? A negative plate. And what do? Repel away. Okay. If the charge is too high, what happens? It goes up. If it's too high, it goes up by a lot. Splatters on the top of the device, don't see anything. So we adjust that a little bit. Do it again, wait for another drop to fall through. Eventually what we do is are able to see that drop come through, change the voltage so that it floats up, and go, oh, don't go up too high, change it back down. And so the drop is just going to sit there and bounce up and down until eventually you found the perfect pressure, and what now happens? It levitates. Okay? There's a downward force. What's that downward force? Gravity. Do we know gravity at this point? Yes. Okay? We know electricity. We know how much current we're pumping into the device. So we can actually calculate what's the downward force of gravity versus the upward force from the electric repulsion to determine the exact charge on that droplet. Okay? Downward force, like if I dropped a marble on your head, you might be like, ow, right? If I dropped a bowling ball, same response? No, the force is different, right? So you would have to know the mass downwards, right? How do you figure out the mass? a scale, how are you going to measure a drop? Through that microscope, you have to calculate the volume of the drop. So you have to know radius, density, not density, all that fun stuff. You're looking at a drop being like, yeah, that's about a millimeter. It's not a millimeter. It's a lot smaller. Okay? To get that mass. What are the odds you did that calculation right? Pretty slim. Probably goofed up. How can we minimize that error? That's a different part of the puzzle, but that's the same issue. Okay? Getting that exact value is going to be difficult. How can I minimize the error in that measurement? Get an average. I do the experiment a bunch of times. So imagine you're sitting in a dark room, little perfume bottle, your eye on a microscope, waiting for this stupid drop to fall through a stupid hole so that you can dial a stupid valve so you can pull out a ruler and measure the size of this drop so that you can determine a charge on an electron. And then after all of that, get no credit for it. Okay? So it's kind of neat. Okay? I like to point it out. It's a neat experiment. So oil drop, Millikan, Fletcher, charge on an electron. Those of you wondering like, oh, I don't think that's all that useful. That would be all the context you would need to be able to answer a multiple choice question. Those 4 words. Okay? They're saying, oh, I'll just read it in the book. It's not in the book. Next. Rutherford comes along. Okay? Now a little bit of interesting history here. Okay? Rutherford's this big famous scientist by this point doing lots of work. To get to being a big famous scientist, what did he first have to do? He had to be a student. He had to be a graduate student in somebody's lab. Any guesses? He was a graduate student in Thompson's lab. Okay. Thompson discovers an electron, comes up with the first model of the atom. Rutherford comes along, says, hey, let me contribute to that. Okay. So how does he go through and do this? So they design this experiment. Okay. We've got this source of alpha particles. Okay. What is an alpha particle? You did the reading, didn't you? Didn't it say what an alpha particle was? You talk to me. So that doesn't count. What did the book say an alpha particle was? Does silence mean you're like, I have no idea what the book said because I didn't read it? I'm going to argue that's not the case. Could easily be wrong on that. I like that you're looking through the book, trying to find where it says alpha particle. That's a good option.
Is it like a helium strip of electrons or something?
Okay, did they say that in the book?
Did it have some type on my notes?
Okay, it's possible they said that in the book. The alpha particle is a helium stripped of an electron, or stripped of all of its electrons. So it's just the nucleus of helium. Did they know what a nucleus was? No. So what did they know an alpha particle was? The first piece of radiation they'd ever discovered. That was it. There was just some form of radiation. We don't know what it is. We know that it comes from these substances, but it just happens. Okay? And we know this piece of radiation is positive because we can see how it responds to magnets. Okay? And we can tell that it has a decent mass due to impacts. Okay? So we've got some information about it. Okay? We've got Thompson's model up top. Pretty much just a bunch of empty space. So what we're going to do is fire alpha particles at it, these big massive things that are positively charged. What are they going to do when they see that atom? They should just pass straight through. Okay? There's nothing of any significant mass. Electrons, if anything, would attract the alpha particle into it. And we should just see our alpha particles pass straight on through. Okay? What are they aiming it at? A piece of gold foil. So they put the gold foil up, they aim their alpha particle gun at this, and then just fire it across and see what happens. One of the stories I liked to tell in the past was that Rutherford didn't like Thompson, because if he had liked Thompson, this would have been his experiment. What just changed? Did they all go through? Did I erase that not going through? What did I erase? There's that thing on the outside. What was that thing? A fluorescent screen. Ultimately, a detector. So my argument would be if Rutherford liked Thompson, that would have been his detector. Because what is he going to see? It only goes straight through. Since there's no detector all the way around, you'll never see it. Right? But because Rutherford was a good scientist, said, you know what, we needed to design an experiment that would actually test for the impossible. So we include the detector all the way around. And when we fire it and we see random pinpricks of light on the other side of the gold foil, something weird is going on. Thomson's model can't be valid because that particle bounced. If there's nothing there, it shouldn't bounce. That's kind of crazy. Right? So what does he conclude based on this?
There's mass there somewhere.
There has to be a mass there somewhere. Not only that, if it was a negative mass, what would have happened if that positively charged alpha particle hit it? Gone straight through or stuck to it. Okay? It would not have bounced. Which means not only is there a large thing with mass in there, it also has to be positively charged to repulse that positive alpha particle. Right? We now have the birth of the nucleus. That's kind of neat. But of course, we've got this question of what are these alpha particles and where do we get them from? Right? We don't have a nucleus at this point. So when we said, oh, it's a helium nucleus, I literally don't know what a nucleus is, and I'm using it to test if I have a nucleus. It doesn't work. Okay? All I know is that I have a particle with a lot of energy and it's positive. Where did I get that from? Okay, where did I get that super active helium from? Because normal helium doesn't do this. Okay? Those fluorescent screens kind of started partially the explosion of this technology because we started to see things that appeared on screens when we didn't have the visual ability to see that radiation. So we see the study of nuclear radiation really drive a lot of this. And in particular, this experiment, that source of alpha particles came from one person. Madame Curie, which is a fascinating story to look into, and I do not give it anywhere near the justice it deserves. Turn of the century, 1900s, do women have the right to vote? No. Do they have the right to do anything other than eat, sleep, and clean? No. And yet Madame Curie is the one that actually contributed to the source of alpha particles for Rutherford's experiment. Without her work, we don't get a nucleus, probably for another 20 years. That's pretty phenomenally cool. Add to that kind of the idea behind science. You cure cancer. What's your motive? What are you going to do right now? Boom, you've got it. What do you do with it?
Patent it, test it.
Patent it.
Open source.
I don't think it's me. No one did that for me, right? Just checking. Okay, patent it. Okay, why would you patent it?
So you get credit for your work.
So you get credit for it. I heard open source. What do you mean open source?
Open source, you give it to everybody, so
Give it to everybody. Okay? Usually the motivations for patenting aren't just so that I get credit, because you can get credit for open source stuff too.
Financial benefits.
Financial benefits. Okay? This is a huge issue within science because particularly pharmaceuticals are like, we have to charge that much so that we can invest in our research. That's why it's there. Okay? Big debate. Okay? There's something to be said for patents and getting credit and getting money where it was deserved. There's also something to be said for getting patents so that you prevent other people from doing that research. Okay? What did Curie do? Effectively open source. Okay? Not only open source, but helped people and gave people the samples that she purified. Okay? That's pretty fantastically cool. So her viewpoint on science was, let's get it out there, so let's make more information available. Make it more widely available, not less widely. That's pretty neat. Coming from someone who couldn't vote. Okay? Add to some of this. There are a couple people in the history of the Nobel Prize that have won 2 Nobel Prizes. She's one of them. Okay? She is the only one to have won 2 Nobel Prizes in science fields. That's pretty cool. Okay? Still couldn't vote. Okay? So this I want to address as a topic for science. We need to be more inclusive and bring more people into these discoveries because observations happen by everybody. Okay? And we need to give everybody the opportunity to hypothesize and test those observations and theories. Okay? So accept those failures and continue through the process. Don't get held back by them. Okay? We can throw in another big failure on it. She was actually Polish, but she did a lot of her research in France. The French National Academy of Sciences did not grant her admission to the science club because she was a woman. They've since backtracked on that after she died. Like, oh no, you were seriously cool. We just didn't want you while you were alive. Okay? So there's been a lot of things holding people back. Okay? Fight through those and move forward. Okay? One of those things that she had, and so I don't want to overplay her and then downplay some of the other contributors here. She had a lot of supportive people around her who were also contributing. The very first Nobel Prize she wasn't going to get. Who was going to get it? Her husband. Her husband said, I will not accept this unless you also give it to my wife. Okay? So there's a lot of support there. Take advantage of that support to advance further on. If you're interested in that story, I do highly recommend you continue to look at Curie because she's a fascinating woman. Okay? So, particles bounced back, which then meant we changed our model and we get a nucleus. Okay? That nucleus is now where I have all of that positive charge. Notice there's 2 colors in that nucleus, right? Yeah, why are there 2 colors? Neutrons. What neutrons? Thompson said electrons and protons. Has Rutherford proved the existence of neutrons? No. He just said that all of the protons have to be in the same space. But what happens when I bring those similar charges near each other? They repel. So Rutherford said, if this is to be true, and we've got evidence to say it is, that means there must be another particle. There has to be a glue holding all of those positively charged things next to each other. Okay, so he was able to theorize and postulate that. Kind of neat. So, give you an idea of some scale before we move further on. Diameter of an atom. I heard a couple people complain, like, oh my God, powers of 10, these things are crazy. I don't even know what's going on with it. Don't feel alone. Nobody knows what the scale of those numbers are. People are like, oh, I totally understand it. Bull crap. Okay? The scale of these atom or atomic structures, both in the negative and if we look at things in the positive, like our national debt, are so massively huge that what do? We invent things to make them seem more manageable. What is our national debt? In the trillions. We invented the word trillion to make the number easier to talk about. Okay? So we're using language to make numbers more manageable. Well, how big of a number can we deal with? Can our human brains really process? What do you guys think?
Like remember?
Just not even remember, think about, be able to manipulate, understand.
We're comfortable with about 250 people.
10. We can deal with 10 because we got 10 fingers. For those of you being like, I can count higher than 10 on my hands, yes, you're more advanced. That's cool. Most people deal with 10 fairly well. Anything higher than that becomes difficult to understand. For those of you being like, that's not true, I can totally understand more. I'm going to go to the store, what am I going to buy? When I buy eggs, how many am I going to buy? I'm going to buy a dozen. I invented a word to describe 12. We don't deal with numbers larger than 10. Okay? So, let's try and put those numbers into a little bit of dimensions that helps us to understand. Let's take a look at the atom the size of the Superdome. Okay? Pick ASU's football stadium because they're closer. Okay? A marble inside that is the nucleus. A marble. Not like a big marble, like a normal marble inside a football stadium. That's pretty insane. That's the scale that we're looking at for these things. Okay? So, Rutherford was able to predict it because we couldn't bring those charges near each other. Chadwick comes along and actually discovers it. Fun bit of history on that. We had Thompson, who was in Rutherford, who was in Thompson's lab. So he learned about atomic structure. Then we had Chadwick, I don't remember the year, 1840s, 50s, discovers a neutron. Whose lab was he in? Rutherford's. Okay. These people were building on each other's knowledge literally from each other's research groups. It's kind of neat. Okay? So what we end with in all of this is this big summary of what our subatomic particles are. You notice that's in a red box, right? Yes, Mike, we noticed that. Yeah. Why would we do that? It's important. You need to know that. Okay? You need to have all of that information memorized. Okay? Because what's going to happen with that is you will see questions in this unit that say, well, what is the charge on a proton? Well, positive. What is the charge on an electron? You're like, oh, that's easy. I don't need to worry about it. In the next unit, I'll ask, what is the charge on this atom? To get the charge on the atom, I would have to know the charge on the protons that were in said atom, the charge on the electrons that were in said atom, and it's the balance of all of that. So these things will build. We're starting easy for a reason. Don't just assume, oh, it's easy, I don't have to worry about it. Right? I've built the class to constantly go upwards. Okay? Anybody want to memorize the mass of an electron is 1 over 1,836? Not really. That's kind of a crappy number to memorize, right? Okay. I've been looking to lose some weight. Okay. So every morning I step on the scale, I see a number. Oh, that's exciting. Okay. And then I read about in a biology class that hair has weight, right? It has mass. So I decide to pluck out a hair, and now I step on the scale. I've now lost weight, correct? Technically. But the balance doesn't tell me that. It tells me the exact same number. Why? Okay. It's the accuracy of the device measuring that is such an insignificant amount of mass that it is effectively 0. So instead of memorizing that stupid fraction, which a couple students have and have then yelled at me for it, I'm not telling you to memorize that fraction. Memorize it as 0. Electrons don't have mass. Okay? Questions? What do we got? I'm not writing the number. No, ignore that. We don't want that number. 0. It was 0. It was 0 times 1 over 1,836.
Okay.
So if you want to do that, you can memorize that.
Gotcha.
0 times that. We okay? So, now our textbook goes into this thing called atomic notation. I get kind of weird and angry about some things. This is one of those things I get kind of weird and angry about. This is not atomic notation. Okay? We're going to address why it's not atomic notation, and we will also try and fix it so that it is atomic notation. Okay? So we got some information up there. We just talked about an atom, right? What is in an atom? Protons, neutrons, electrons. That's what's in an atom. We get those 3 particles, right? Take a look at that atomic notation. You can look at the words or you can look at the symbol down below. What subatomic particles are described? Protons and neutrons. Does it say anything about electrons? No. That's because this is not atomic notation. Okay, we'll call it atomic notation, and it's a crap name. What is it? It's only the protons and the neutrons. Well, where are the protons and the neutrons? In the nucleus. So this isn't atomic notation. This is nucleus notation. That's not bad. Nuclear notation. Okay, we're concerned about what our nucleus looks like. Okay. Why would I care about what my nucleus looks like? If I knew that, I wouldn't be taking this class, you jerk. What word could I add after nuclear to make you guys freak out a little bit? Right? So I'm going to care about nuclear notation if I'm concerned about nuclear bombs. Okay? Well, what's the chemistry associated with nuclear bombs? Or nuclear radiation? Whoops. That erased weird. What element? Uranium.
Plutonium.
Love having a periodic table under the projector. Uranium, plutonium.
Hydrogen.
Different. Okay. Where are those elements on our periodic table?
Down at the bottom.
At the bottom of the periodic table. Okay. What does that mean about their size? They are massive. When we're talking about nuclear notation, this is largely for nuclear scientists, people studying nuclear bombs, people studying nuclear energy. Okay? And we're looking at massive atoms. Why massive? Because those atoms produce nuclear energy. Okay? And it is in particular their nuclei that is producing that. Okay? The bigger the nuclei, the more likely I get radiation. What's in the nucleus? Protons and neutrons. I'm now a nuclear scientist that is trying to study this. I want to create a notation that allows me to quickly look and identify that is a radioactive species I want to look at. What's the very first thing I want to see in my notation?
The mass number?
The mass number. What's the mass number?
The protons and neutrons?
Said the most important thing was the size of the nucleus. The nucleus is dictated by the protons and the neutrons. The very first thing that shows up in my atomic notation is the mass number, which is literally the sum of the protons and neutrons. That's why we write it there. Okay? It is designed for a nuclear chemist. Okay? So that's what I'm going to write in that symbol. Okay? Protons and neutrons. Okay, what else might I want to know? How about the element itself? That could be useful. I'm pretty sure that's the wrong number. Let's try this. So if I write 238, what does that mean? Okay. It's a number. How would I know that's tied to an individual element? I'll probably need to see. How about the next thing that I encounter when I read left to right, top to bottom? So maybe for the record, is that how we all read? You start in the upper left page, you read left to right, and then you move down left to right. And you're laughing, and yet, when I asked what's the next thing we read, what did you say? I don't know. Dude, you got it. And worst case, what happens? You get it wrong, and what happens? We all get a laugh, including you, and we move on. It's cool. So, first thing we need to see, it would be symbol. Okay? So we could write 238. Where'd it go? Cool. And we could write U. Now we know we're looking at uranium with 238. The next thing I could write underneath it would be the atomic number. A couple people have periodic tables, and I already forgot the number. Damn. Is it 88 or 92? 92. So let's make sure everybody's on the same page, which is going to be illegible, but we'll try it anyway. If I tell you the symbol uranium, we see that 92 in blue, right? What's the number we see underneath? 238.092. Is that the mass number? What did I say the mass number was for my symbol? 238. So is that the mass number? Did I write 238.0929? No. Is that the mass number? No. It's the atomic mass. We'll deal with that in a second. 92. Did I write 92? I did. Did I need to write 92? What is the atomic number for carbon? 6. Atomic number for, maybe I should not be, well, we'll test it. Xenon.
54.
54. Atomic number for rubidium. 37. For those of you being like, I don't remember those symbols, you should start working on memorizing those. Admittedly, I think I threw ones that were harder because the rest are covered by all the text. Okay? The atomic number is directly tied to the element. If I know the element symbol, what do I know? The atomic number. Which means, is it useful to include the atomic number? What's the atomic number for uranium? How do you know that? It's on the periodic table. When do you have a periodic table? Under most circumstances that aren't in this classroom. People are like, never. Okay, now you're a bad chemist. You always have a periodic table. You will never be without a periodic table. Where's your periodic table? You've got a phone. It's there. You should always have it. Right? Which means, is it necessary to specify the atomic number? As soon as I know U, the atomic number is readily available on the periodic table. I don't need to write it. Is the mass number on the periodic table? No. We had a different number written on the periodic table. It was close to 238, but it was not exactly 238. Okay? So the mass number is not on the periodic table, which means it would have to be specified. Okay? I now have a notation that allows me to quickly see 238. Damn, that's huge. Must be reactive. What's the element? Uranium. Done. I draw all the conclusions I need. Because scientists like to make things confusing and make you do extra work, we also threw on that atomic number and said that we had to include that down in there too. Good thing I color-coded that so beautifully. Let's try that again. Okay. You are responsible for knowing where those numbers get placed. You now have the context for why we place them there. The mass number we place up at the top because this is nuclear. I care about the nucleus. I want to know what's in the nucleus. The next thing I encounter is the symbol. Okay? Next most important thing. The last thing that I could find if I just looked at a periodic table is the atomic notation, or the atomic number, the number of protons. Okay? We've now ranked the order in which you should be reading that. That should help you process where those things should get placed. Okay? Did that account for all of the subatomic particles? No. Okay, so let's account for the last subatomic particle. What's the last subatomic particle? The electrons. Sorta, kinda, the electrons have already been specified in this. Okay? Where did I specify the information about neutrons? That was in our mass number. Yes, it's convoluted with the protons, but what could I do? Crap, 14? Ta-da, now I know the mass, the amount of neutrons. Make sense? It's even organized so you could just run a simple calculation to get your neutrons. So our neutrons are found in the upper left. Where are our protons? Lower left. Okay. If I gave you a symbol, is one of those corners already occupied? For those of you wondering about that one's a tricky one. What was our formula for water? Is one of our corners already occupied? Yes, which corner? The bottom right, and what's in that bottom right? For water, it's 2. Be more generic. The amount, the quantity. It's the quantity of the element in our symbol. Okay, which means, where am I left to specify the electrons? The top right corner. That's where the electron information is stored. Okay? But it's stored in kind of a goofy way, similar to how we store the neutrons. Okay? When we looked at the neutrons, they were stored in conjunction with the protons. Our electrons are also going to be stored in conjunction with the protons. And we'll call that a charge. That charge is our protons plus our electrons. What is the charge on a proton? Positive. What is the charge on an electron? Negative. So when I looked at that uranium, let's see if I can pull off a color coding. 92, 238. What was the charge? Where should that charge be written? In the top right corner. What is written in that top right corner? Nothing. What is our numerical representation for nothing? 0. How many electrons do I have? 92. Every so often someone will say, well, there's 0 because you wrote a 0. It's the balance of our protons and electrons. If our protons are positive, to completely balance out the electrons, I would need an equal amount. How many electrons would I have for this uranium ion? 3. Okay, let's work with that one first. I like that one, and thank you for shouting that out. Okay? So let's start with that. Protons, electrons. What was our amount of electrons? We said 3. What are the charge on electrons? -1. How many protons do I have? 92. How do I know it's 92? That's the atomic number. Okay. How do I know it's 92? Because it's uranium, because of the symbol, I can look to the periodic table to know it's 92. So there are 92. What is the charge on a proton? What is the overall charge when I add that all up? For those of you being like, I can't do that in my head, I'm right there with you. 92, I'm going to distribute that, minus 3. That would be a positive 89. Is that what the charge was on that uranium? No, it was negative 3. I think I heard someone shout out, it's 89 electrons. (92) minus 89 would be positive 3. Great, we got 3. But the wrong sign. Process those pieces. How many electrons do I need to have? 95. I have to have 3 in excess of whatever the protons are to ensure I get that negative charge. Okay? Why walk through this? People tell me that negative charge is not a big deal. They can deal with it all the time. For those of you that struggled with this, you're wrong. Negative charge is probably the most difficult thing for students to grasp and manipulate through all of chemistry. It will haunt you through virtually every calculation we run. Be very careful with anything that is a negative sign. Okay? Charge is dangerous. Don't stick forks in electrical outlets. What do we think? We now have an atomic notation. Accounts for our protons, our neutrons, our charge, and we even added an extra specificity for quantity. Easy? No. Good honesty. Okay. Might be useful to have some practice, right? Maybe. What's the element? How do you know it's silicon? You have memorized that the symbol for silicon is Si. For those of you that haven't memorized that, that is, I think, one of the important ones that you should memorize. So you should start working on that. The atomic number is 14. That might be a little bit more challenging if, say, we had done something more appropriately, like erased the 14 and then also erased that information. Right? So you do need to know where those pieces of information are located. Does that make sense? Okay. So 14, what does that mean? There are 14 protons. Right? Because I think I've got this stepped. Let's see what happens. Okay. A mass number of 29, what do I know?
15 neutrons.
Okay. I have 15 neutrons. Okay, some people were able to do that math really fast. You suck. 29 is the total number of protons. Whoa, that was a weird flash. Total number of protons and neutrons. So if I wanted to solve for the number of neutrons, what would I have to do? Subtract. 29, how many protons? 14 plus neutrons. Okay, subtract 14 from both sides. We get 15 neutrons. Yeah? We cool? Do you feel better? Because I think that was you that said no, it sucked. Okay. I really like the last column on this. The rest of that you guys should be able to figure out. But let's think about the meaning. So I'm not going to walk through all the other ones. If I tell you, oh shoot. Should we be dangerous? Maybe somebody gets it. We'll go ahead and do it. What is the meaning of each individual number? Man, that's like an explanation for why carbon's awful, right? Okay. What is the meaning? If I tell you 6 electrons, what could you tell me? Can you tell me there's 6 protons? Okay, I just said 6 electrons. Okay. If I also say there are 6 electrons on an atom and it is neutral charge, now 6 protons make sense. Okay, that's a lot of extra information. I just said 6 electrons. Okay, so the meaning on that is a little bit challenging. Okay, so I would argue we should start with protons. What does it mean when I tell you 6 protons? Not necessarily anything about neutrons. For those people with a periodic table in front of them, take a look at what it means to have 6 protons.
Oh, it's carbon.
If I tell you 6 protons, you now know the element. Okay? Protons define the element. Okay? That's the meaning. Okay? That has to be my starting point. If I've got 6 protons, I know I've got carbon. Okay? Now let's say I have carbon and 6 electrons. I said it was carbon, so I already know it has 6 protons. What if I tell you it's carbon and it has 6 electrons? It's neutral. What if it had 7 electrons? It's -1. See that negative sign? Okay. So if I tell you the element and the number of electrons, you've now defined the charge. Okay. So it requires a little bit more information because I have to define that element. Okay. What do we think for the neutrons? I don't like the word weight, but yes. Define mass. Okay? We now have a way to interpret a numerical value for an object to draw some other conclusions. That's pretty cool. Okay? So, what happens if instead of it being 6 neutrons, it was 7 neutrons? What am I looking at? I'm looking still at carbon, but it has a different mass. Because it's still the same element, I can't change the name of the element. It must still be carbon, but I need to add some other qualifying information into it. That extra qualifying information is, I call it an isotope. Everything is an isotope, as far as I'm concerned. Not everything has multiple isotopes. Okay? What do I mean by that? Carbon has carbon 12, carbon 13, carbon 14. Okay? 3 different isotopes. Wish I knew one of the elements that didn't have any isotopes. Let's just pick one. Let's call it vanadium. Why not? Vanadium just has 1 type. It doesn't really make sense to call it an isotope, but I mean, it technically is. It's just the single element. There's just no other possible combination of neutrons. Does that make sense? So let's go back up to our table where it says defined mass. Yes, it defines mass, but we could change mass to be isotope. Okay. How would I write that out? So the first case is where it was 6, not 67. We'll say 6 or 7. I'm still looking at carbon and carbon. Okay. Or for that matter, we could do carbon and carbon. How would I know that I was looking at an isotope of carbon? Because of the protons?
That's how you know you're looking at carbon.
You're shaking your head. I know I'm looking at carbon because it has 6 protons. I want to know I'm looking at an isotope. So you're shaking your head because what would need to change?
It would be like raised to a positive or negative.
Okay, raised to a positive or negative. What I'm hearing with raised, I'm hearing something placed there.
Yeah, like gained or lost an electron.
Gained or lost what?
An electron?
An electron. Electrons are defined by charge. What are we looking at? Isotopes. So it's not going to be electrons, it's going to be neutrons. Where do we find the information about the number of neutrons? The mass number, which was specified where? The top left corner. So for our red carbon, we would write that as 6C, right?
No.
No, okay. What did I screw up?
You forgot the protons.
Okay. Or I forgot the neutrons. That conveniently I picked one that had the same number. The upper left-hand corner is the mass number, which is the sum of everything that has mass. Which particles had mass? Protons and neutrons. In this case, 12. What if I had 7 neutrons? 13. So I could see it if I had written it in atomic notation. What if I didn't write it in atomic notation?
You'd be able to tell by looking at the neutron neutrons if you know.
As a hint, I'm attempting to fill it in right here in that corner.
Oh, isotopes are written like carbon and then the number next to it.
Carbon with a number next to it. Yes, we've identified the element. It is carbon. That's effectively specifying that symbol. And then the number next to it. What number should I write next to it? Okay. I'm hearing a suggestion to go for 13. So that would be for our purple one. What would be the other number that we could possibly write? Think for the red one. 12 would be following the same pattern as our 13. What's the other number that we could write there that doesn't follow that pattern? 6. And the red one, what are we counting for that 6? Neutrons. Not protons. Protons are specified by carbon. Yes? And the purple one, why are we writing 13? That's our protons and neutrons. Which notation do you think would make more sense to use? Red or purple? Purple, okay. Why? It's not giving you more information because this 6 is saying I have 6 neutrons. By writing carbon, how many protons do I have? 6. I get the exact same information in both cases. Okay? I heard a suggestion, well, the 13 is the sum of the protons and neutrons, and the 6 is just the neutrons. So I don't quite accept that as a Y either.
You already know carbon has 6 protons.
So shouldn't it make sense to go with the red one, not the purple?
I think so.
I think the red is too obvious. You already know that the 6 has you already know that carbon has 6 protons. You can assume that they're
That's an
talking about
interesting answer.
protons. So like when you have the carbon, you know that you're talking about protons and neutrons. You can subtract the 6 and find the 7.
The red one's too obvious. We can't possibly pick the obvious answers. Okay? I kind of agree with that. But what I would argue is, did we already create a system where we've specified mass numbers? Yes. Let's not create a new system that we would also have to learn rules behind. Does that make sense? Which means when we write it out, that should not be carbon 6 in red, that should be carbon 12. To represent the mass number, because we've already used a system when specifying our neutrons to always include the protons with it. If we now start to separate the neutrons out individually, we've created another way to represent it that isn't adding value. Do you understand? So we're looking at how language builds and trying to make sure we follow off the same patterns that we've established in previous cases. Make sense? Cool. So, isotopes. Neutrons define our isotope. Hydrogen, we have protium and deuterium. What element did I say that was? Hydrogen, and yet I'm calling it protium. Where did that come from? It's an isotope of it. What was the isotope name for carbon-12? It was carbon-12. That was the name for it. What should the name be for protium? Hydrogen-1. Why do we call it protium?
It's fancy.
One option is it sounds cool. Don't put it above scientists. Scientists are the same people as you. They go, that sounds cool. Let's do it. Okay? I would argue that it's probably not coming from that. It's that we used it so much that we created a name to represent it. Okay? Does that name have meaning? What is in a hydrogen nucleus? In fact, a hydrogen 1 nucleus, I should say. A single proton. How many neutrons? None. So what's in the nucleus? Just a proton. So there's only one proton. So I could call it protonium. Let's get rid of the on and we get protium. What happens when I move to deuterium? I have a proton and a neutron. Protonium is just weird. How many particles was that? 2. We're about done. Dropping a deuce. Deuterium. Okay, representing the 2 particles. Way to make everybody uncomfortable, Mike. You're welcome. Okay, so those names aren't things you have to memorize, but recognize you might see them. There are different ways to represent them. What we're going to end up looking at when we come back on Thursday is doing all of the fun math and quantification that runs behind these.